Hello everyone, I hope you're doing well. So we have not been able to post the Geeks for Geeks problem of the day for a few days, and I also made a community post about it. But now you can expect us to be a little more regular, and if possible, I'll also try to update the GitHub repository and update all the problem of the days which were not solved before. I'll update the source code for it. You'll also find the solution for today's video in the description. But before that, you can also watch the whole explanation and understand how the problem works. So let us quickly start with the video. And in today's video, we're going to discuss the Geeks for Geeks problem of the day. And today's problem is shortest path using at most one curved edge. And it is a hard level problem. So the problem is we have been basically given an undirected graph with n vertices and m edges, right? And in this graph, there is a special edge called a curved edge, right? We have our regular edges like normal, and we also have some curved edges. Now, whenever two nodes or vertices are connected, they have both a normal edge and a curved edge between them, right? So W1 denotes the weight of the normal edge and W2 denotes the weight of the curved edge, right? Now what we have to do is we have to go from source to destination by using at most one curved edge. So the property at most is very important here. At most means we can either take zero curved edges or take one curved edge, right? So let me just quickly explain you the problem, how this works. First we'll discuss the sample test case. So in this particular test case, like this is given here. So this is the sample test case. You can see that 2 is the source, this is the source, and 4 is the destination. So this is the source and this is the destination. And according to the problem, there is a straight edge between 2 and 1, and there is a curved edge between 1 and 4, and this is the shortest path. So this is 1, and the total distance is 2. So our answer that we have to output is 2. So we have to form such configuration such that we can go from A to B using at most one curved edge, and the total cost of the total path should be minimum. So this is the basic problem. Now how do we solve this? First of all, we have a case where we use case 1, use zero curved edges. Use zero curved edges, right? So the problem statement says that we can use at most one curved edge, and we can obviously form a case where we are using zero curved edges, right? So if we are using zero curved edges, if we remove all these curved edges, if we remove all the curved edges from the problem statement, then the problem reduces to a simple graph problem where we have to find the distance between two nodes. And this problem can be easily solved with any shortest path algorithm such like Dijkstra's algorithm, right? So case 1 is easily solvable. You can solve it using shortest path algorithms. One such algorithm is Dijkstra algorithm, right? So case 1 is very sorted. Now we have case 2, use one curved edge, right? And these are the only two cases that we will have in our problem. So we need to focus more on using one curved edge, right? So I'll give you an example how this problem can be easily solved. It's just a bit of observation. So for example, if I have my source here and I have my destination here, right? And let us take two random nodes x and y. So this is x and this is y. We are going to use exactly one curved edge, right? So we need to find some nodes between which some curved edge exists. So let us assume that there is a curved edge between x and y, right? So these have the curved edges. Now how can I solve my problem? I want to go from source to destination using the curved edge between x and y. The problem is very simple. What you can do is you can just draw one line from here, and you can draw from one line from here like this. So let me just put some arrows. So essentially what you're doing is you're going from source to x and from y to destination, and you're also going from x to y using this particular curved edge. So if you can only use one curved edge, that means all the edges that are between source to x and all the edges that are between y to destination are straight edges, right? So we can easily find the distance between source to x, right? And we can easily find the distance between y to destination, right? How we will find it? Let me just explain you. Since we have already computed the single source shortest path for our source, right? Like in the previous example, when using case 1, when we were having 0 curved edges, what we were doing is we were finding the single source shortest path starting from the source, right? So we must also know the shortest path of x from source, right? So this much part we know, already know. Now the problem is, how do we find the distance of destination from y, right? Finding that distance of destination from y is a bit of a task, but it is very easy if we know one property of an undirected graph, right? So the special important property is, if the graph is undirected, then the distance of a to b is equals to the distance of b to a, right? If the graph is undirected, and no matter whether it is weighted or unweighted, the distance of a to b will be equal to the distance of b to a. So what we can essentially do is, since our variable y or our node y and x are changing, what we can instead do is we can calculate the single source shortest path for our source and single source shortest path for our destination. Once we know the distance of all the nodes from the destination, no matter how many times this y changes, we can always find the distance between y and destination in just constant time, right? So we were already calculating it for the source, the single source shortest path. Now we will also calculate it for our destination, right? So no matter how many times this variable y changes, the distance of y and destination can be calculated in O of one time. So what we are doing is, we are calculating the single source shortest path for our source as well as the single source shortest path for our destination, right? So now we know the distance of source to x, right? We know the distance of source to x. We know the distance of this curved edge. Let us just write it as curb. We know the distance of y to destination. So we can find that find the total distance between source and destination using this particular curved edge, right? So this was just one configuration of attaching these 2 points, source and destination. Now, and I will show you an alternate configuration. So this is just one way of doing it. Instead, what we could have done is, we could have connected the destination to x and then connected the source to y, right? This was also possible. So what we essentially have to do is, we have to take the minimum of these 2 ways to connect source and destination, right? Earlier what we were doing is, we were connecting the source to x and then destination to y. But now what we are doing is, we are connecting the source to y and then the destination to x. So we will go from source to y, then y to x, and then x to destination. So this will be our flow. In both of the ways, we are using the curved edge between x and y, and we are connecting the source and the destination. So this will be the whole explanation of case 2, where we are using one curved edge, right? So for every curved edge, we will decide whether we want to include this particular edge or not, right? If we know we are going to use the curved edge between x and y, then we have 2 ways of connecting source and destination. I've already discussed those 2 ways, and we will compute the minimum answer for all these configurations. First of all, we will deal with the case when we have 0 curved edges. Then we will deal with the case when we have one curved edge, and we will try to fit all the curved edges. Like we have been given an edge list, so we will try whether we can fit this edge, and then the next edge we will try it for all the edges, and we will find our minimum answer. So this was all about the code solution explanation. Let me just repeat it once again. So we have been given this undirected weighted graph, where there are some special edges called the curved edges along with the standard edges, right? We can use at most one curved edge to go from our source to our destination, and we have to find the minimal cost of doing this operation. Now we have divided our problem into 2 cases. The first case is when we are using 0 curved edges. Now this particular case can be easily solved with the single source shortest path algorithm, where we can find the distance between 2 nodes in a simple graph. In a normal graph, and we can here we can find the distance between A and B using any single source shortest path algorithm. Right, now we have our case 2. What we are doing in case 2 is we are using exactly one curved edge. Right, the problem discussed that we can use at most one curved edge. So in case 1 we are using 0 curved edges, and in case 2 we are using one curved edge. Now if we are using one curved edge, we have to first select the nodes. What are the nodes between which we are using the curved edge? So let us say that we are using the curved edge between x and y. So what we want to do is we want to connect the source and the destination in such a way that x and y is between the path, right? Such that x and y is also included, so that we can use this particular curved edge between x and y. So we discussed two ways of using this curved edge between x and y. The first way is to connect source to x, then x will be connected to y using the curved edge, and then y will be connected to destination. So this is one way of doing it, right? The another way of doing is that source is connected to y, is then from y we go to x, and from x we go to destination, right? So for each and every curved edge, we have to find the minimum of these two edges, and we consider the minimum of all those values we have computed till now as our answer, right? Now let me show you the code for this problem. So initially what we do is, so I'm just more comfortable with using the adjacency list rather than the edge list. So the input has been given as edge list. So for using the single source shortest path, we will be using the adjacency list. So first of all, as soon as we start the problem, what we do is we create an adjacency list. So this list is called graph. Now we have to convert this edge list into an adjacency list, right? So what we do is this is simple conversion. For I traverse each edge and I initialize my new item, and I just like add it to my adjacency list. So what I'm doing is I0 and I1 had the variables A and B, right? The source and the destination. So first of all, I'm inserting it in I0 and then I'm inserting it in I1, right? So here I don't need any curved edge, so I'm omitting the information of the curved edge. I'm just using the two nodes that we currently have and the distance between them. So first of all, I just insert I0. So in I0, I insert I1 and I2. I1 is the destination and I2 is the distance between those two nodes, right? And similarly, in edges of I1, I'm inserting I0 and I2 again. So these I1 and I0 get swapped because now the source has become the destination and the destination has become the source, right? So from I1, I can go to I0 and the distance will remain same, that is I2. So this is just forming of a simple adjacency list. Now I initialize two vectors dA and dB. So dA will have the single source shortest path with the source as A, and dB will have the single source shortest path with the source as B, right? So this is what I'm doing. So here you can see I've initialized my source and destination. You don't actually need the destination here. The source is important just. So as you can see here, the source is A and here the source is B, right? So this part is just Dijkstra's algorithm. In the helper function, I have implemented Dijkstra's algorithm. So if you already know, then you can skip this particular part where I'm explaining this Dijkstra algorithm. If you don't know, I'll just quickly go through what is happening here. So I've received the source, I've received the graph, and I've received the number of edges. I initialize my distance vector. So I've initialized with the variable answer. So answer will contain the distance of all the nodes starting from the source node, with the source node as the source. So I've initialized its distance as 0. I formed a priority queue with the pair, right? So the first element in my priority queue will be 0 and source. So 0 denotes the distance of the current element with respect to source. So the distance of source from source is 0. So that is why it is 0, and the current element is source, right? I just push it into my queue, and I just I get the current node as node and the current distance as D. I go through all the elements, or I traverse the graph node. I just look for all the nodes to which I can go from the current node, and I save its value, the node that we are visiting, and its distance from the current node. So if the distance of the current node plus the distance between the current node and the child node, if we add these two values, if these two values are smaller than the distance of the child node itself, then what we just do is we update the distance of the child node and push it into the queue again, right? So this is the simple Dijkstra algorithm what we are implementing, and at the end we can just return this distance vector. So once I receive the value of all these nodes, I initialize my answer as dA of B. So what is this dA of B? Now dA, the vector dA had the distance, single source shortest path distance of all the nodes starting from A, right? So starting from A, the distance of B is the simple single source shortest path distance. So for example, here A was 2 and B was 4. I just found the single source shortest path without using any curved edge. So this is the part where this is the part where I'm actually dealing with case 1. So this is the case 1 part complete, where I'm just finding the single source shortest path without using any curved edge, right? And in this for loop, I'm just implementing the case 2, where I'm trying each and every edge. I'm just going through the edge list and I'm trying each and every edge whether I get to find out whether I get a better answer or not, right? So here I'm implementing the part 1 of that case 2, where I'm just finding answer is equals to minimum of answer comma this particular thing. So if you carefully observe, what I've done is I have connected the source. A and B are the source and destination respectively. I've connected A with the first node X here and the distance between X and Y here, and then I have connected the destination B with the Y node, with the node Y. So I'm just using the same terminology X and Y as I have used in my while explaining the solution. So I'm using the same terminology here so that it is better for you to understand. So this is the distance between source and X. This is the distance between X and Y using the curved edge, and this is the distance between Y and our destination, right? Similarly, I've just inverted to calculate the answer second time for the part 2, I've just inverted those roles. So here I'm connecting the destination with X. If you carefully see, it is dB. dB means the destination. So it is the single source shortest path from the destination to X. Then I'm connecting the distance between X and Y. And then I'm using the distance of the source to Y. Right. So this is the whole explanation of this problem. And at the end, what I'll just do is I'll just check whether my answer is equals to 1E9. So why 1E9 specifically? Because here I initialized my answer variable with 1E9, right? So I'm just checking whether this denotes that we have not found any path, and in this case we'll return -1, otherwise we'll return our found answer. So this was the whole explanation, and I hope that you guys were able to understand the solution. If you guys were able to understand, you can show your appreciation by clicking on the like button, and you can also share this channel with your friends. We'll be sharing these videos regularly from now, and till the next video drops, keep coding, stay safe, bye bye.